Okay, so welcome to the EOMA68-A20 memory upgrade. This is actual size of the board, and that's approximately the size. Basically, I wanted to show you what has been added. This is pretty stunning. You can see here there's the processor, and then there's 4 RAM chips. Alright, if I zoom in, you can see here it's starting to take shape, easily visible. These are the pads on the BJ pads. Those are 0.65 millimeters apart, which means that you have vias in between. Let me zoom right in. Right, so that is a via, so the track goes from the BGA pad to a via on the top layer and then through to the bottom layer, which is in blue. Now the pin that was missing that we had to add was this one, SA15. Because previously the design that we weren't actually aware that the A20 could actually do 2 GB of RAM using 4 what are known as ×8 RAM chips. So it's a 32-bit wide memory address. So you've got on this side, you have 8 data lines here. You have another 8 there, another 8 here, and another 8 out on there. So it's a total of 32 bits. The only other arrangement we've got is the ×16 one. So there's 2 RAM chips, which takes up a lot less space, but the cost of the 1 gigabyte or 8 gigabit DDR3 ×16 RAM chips is enormous. It's $9 each, so it's $18 of RAM. Whereas these ones, you can see the white outline is the actual size of the chip there. Those are $2.95, so it's a total of $12. Now the irony is I was going to convert to the other form factor for the other type, but then investigation of the price, decided to leave this design as is and add that one thing in. Now I'm just going to one address line in, extra address line. So those blue lines, the beautiful curves, were what the design was like before. And unfortunately, because this program can't cope with moving those and re-adding them, it just removes them. The push and shove has just pushed all of these over, and it was like these kinds of curves here, which have been added by the designer who did this originally manually. Did a couple of thousand curves. You can see on here these yellow ones. This is the inner layer thing. He added a curve there and there, there and there, there and there, on every single one of these tracks. I mean, it was beautiful. Let me show the inner layer. There we go. This is why EOMA68 exists, because this is horrendously complex. I mean, it takes weeks to do this properly, because the rules on DDR3 are so complex. And this is a 6-layer board. So, you know, if you can avoid having to do this and just concentrate on get on with the job of doing a simple 2-layer board where the only thing you have to worry about is USB single line of differential pairs, you're much more likely to succeed in a much shorter period of time. It's the whole purpose of why single board computers exist in the first place, but they're specialized sort of supernova lifespan. So anyway, so these RAM lines, you can see they wiggle. Alright, they come out here. Alright, these ones come out here. Let me put it back to the top again. Where are we? Yep. Right. Then you can see all the wiggling stuff. Basically what that's doing is it's making sure that when the tracks arrive, they're all completely parallel. Alright, and they're all exactly the same length. Okay, so these is differential clock pairs. This is differential pairs. What's the name on those? Can't see it, I think. Yeah, SDQ S0 hash and SDQ0. Okay, so that's data something. I don't know. But the designer who did this, he put all of those at exactly the same length, so they're 945 thousandths of an inch to 947 thousandths of an inch. So there's 2 thousandths of an inch difference between all the lengths of all 32 lines, which is phenomenal. Now, fortunately, there's a little bit of leeway in address lines. So what is a thing? So you only need 3/100ths of a 3/1000ths of an inch flexibility in those, leeway in those. But what he's done is he's branched them out into the middle here, in a staggered line across like that. Then he's branched them out to the middle here, and then gone left and right. So there's a whole series of vias in between from about here to here. You can see that cursor, just I'm moving it, I'm going to use my finger instead. From here to here there's a series of vias, and then there's a yellow one that splits across there, and then a blue one on the top line which splits right across there, because you had to bring the tracks in on the thing. It's the same on the other side. So in this way he's managed to keep the address lines pretty much exactly the right length as well. To really think, you know, within amazing tolerances there. There's the one that where it goes. So the yellow goes left and then splits up and comes up onto the top layer just at the right point to go into the. That's from bits where I hadn't needed to do any push and shove on the curves, the beautiful curves that previous designers had made this, so they survived. Now, address line 15 comes in somewhere around here, so I had to like move stuff up and push stuff down here, alter this thing. The cascade effect was just, I mean, it was ridiculous. Made a real pig's ear of it if it was design. It's like, no. But it's not like I had much of a choice. So you can see, where is he? Where is it? SA15. There we go. This one here had to that one had to put in. So that I had to move that, and that to get this and swap those around and think, oh my goodness me. But I did it. So anyway, yes, hooray! We have 16 address lines, SA0 to SA15 now. Whereas and so thank you very much to Tom Cuby and Prince from Cuba Board Rackstar, I can never pronounce, RADXA, I think it is, for discovering this and finding it, and for publishing the schematics so that I could also do the same thing and add in this address line to get 2 GB of memory. Thank you very much.